from the previous presentation, we heard about we are at the golden age of maps. And as you know, I want to talk about that we are at the golden age of Earth observation. And actually, it's very convenient to be the last keynote speaker of the day, because I don't have to highlight that we now have a game changer for our Earth observation research. Here you see the Copernicus program of the ESA, where we have the Sentinel satellite fleet. They are producing 15 terabytes data per day, and until 2030 we will have 140 petabyte of data that is free and open to everybody. So we will have really the enormous opportunity that we did not have before such data became available. And it's also important to mention another aspect, which is the blooming of the new space economy. So this is just an example of the Planet Lab. So you know that they have more than hundreds of these doves, which is satellites like this size. And of course, if you think about image quality, it's not comparable to our very expensive satellite, but they produce basically every day a global coverage. So this temporal frequency is very, very precious for a lot of applications. Together with the big data, we also need a new analytics methods. And that's why we need AI for EO. And well, I'm using AI because, you know, this is a PowerPoint, it's not Python. Otherwise, I would say it's machine learning. And my claim is we actually, because of the high quality requirements of EO and also the diverse application we serve, we really need innovative and EO specific AI research. So if I talk about which kind of competence we would need to have, here is just several important fields I want to mention. The first one is about information mining. So now we all have tens of petabytes of data, which is free and open to us, which is continuous growing. It's now really important to change the perspective that we should be able to really index the data according to the semantics, not anymore just according to the geolocation. So if you would like to do, for instance, water reservoir, then you will be able to figure out all the data which is relevant for you. And what is also important is that you should have methods which can unsupervised, if not possible, then weakly supervised way to be able to detect changes in the data as well as novelty, which is you can also call it anomaly in your data. Then you don't have to produce the tons of data, which is becoming more and more. And the second point is machine learning and deep learning. And you know that classic analytics methods would not be sufficient. You need more and more data-driven knowledge discovery, refer to the fourth paradigm. And I will talk a little bit more about this later. And the third thing is data fusion. Maybe 10 years ago, if you talk about any geoscientific application, you will be happy if you have any kind of sensor that provides you data. But nowadays, no matter what you do, you will have radar data, optical data, and many other data sources that are available there. Then the question is, how could we use a smart way to get out the complementary information to serve different applications? This is, of course, also very important. And the last but not least, we do not yet have, let's say, completely flexible cloud solution. Nowadays, if you want to do global change research, you are easily dealing with petabytes of data. Here, of course, then big data management and also high-performance computing is very essential. Well, let me say a few words more about machine learning and deep learning. And this is an opportunity where we had the chance to give an overview about the development about deep learning and remote sensing about 2 years ago. But what I want to mention is just one single figure, what we did as paper statistics related to the topic. So basically, you see how everything started from 2014, and the number of papers has been increasing. I'm not sure if it's exponentially, but at least it's more than linearly. And if we add the numbers of last year, I would have a blind guess of more than 1,000. We will check if this is true. Through all these thousands of papers, I have seen people try to approach the field from two corners. There are computer scientists who try to use very fancy methods and try to take out, for instance, RGB channels of our precious multispectral, hyperspectral data to do recognition tasks. There are also remote sensing scientists who try to download pre-trained pre-trained networks to process SAR data. I think, in my personal opinion, we need both. We need an interdisciplinary approach. And above all, we need to understand actually what makes deep learning approach special in Earth observation. So here I'm just sharing an incomplete list of the characteristics we have to take care. For example, in the vision community, we are to a great extent talking about classification and detection problems. But this is obviously only really a small fractions of the problems we have in Earth observation. What we usually have is we need to retrieve physical and biochemical variables, and also we need a very high accuracy, and the results should be reproducible. And also because we are doing measurements, basically it's not enough that we get a very visually appealing result. We need an error bar. So any measurements with no error bars does not make sense. The good thing is we have actually a decade of expert knowledge that we can use. This means we don't need to learn from scratch. And we also have, compared to the image from the internet, we have very well controlled data acquisition. So we have radiometrically, geometrically, and also spectrometrically very carefully calibrated data. We know the statistics of data. We know sometimes even the signal-to-noise ratio. And our data is much more sexy, so it's not really just an RGB image. It's 5-dimensional. We have SAR, we have LiDAR, multi-hyperspectral. We can even include GIS data, OpenStreetMap, open data, citizen science data, and etc. So our data is basically 5-dimensional. X, Y, Z is the geolocation. T is we have the time series data if we are talking about the Sentinel series of data, and we also have different wavelengths. And but in Earth observation, I think is similar to any kind of other use cases. We are usually lack of sufficient training data. So these are the actually a few of the characteristics we always need to think about when we start to doing AI research in Earth observation. And here I just show you few selection of the tailored architectures we developed for a wide range of problems. We have been developing methods, for instance, for detecting, tracking the cars, vehicles, for building settlement mapping or change detection, data fusion, etc. This is what I usually call our deep less zoom. And today I'm not going to talk about these successful examples. And after I share the research agenda we have so far, I will really just focus on two things. Well, what is our plan? So basically, when we're talking about AI for EO, my claim is that we should not use this technique to do the things we could do yesterday, but 2% better. Instead, we should simply focus to tackle real societal grand challenges. For instance, provide geoinformation for monitoring urbanization process, provide indices for the UN's SDG goals, or provide geoinformation for climate research. And under this umbrella, there are, of course, a lot of problems where we need generic methodological development. And here, for instance, what has already been discussed a lot. We need to re-implement physics-based and also domain expertise to this data-driven type of approach. And the second point is currently in Earth observation, we're still staying at the stage where we try to recognize objects, materials, to get some geoparameters, but actually we should go beyond from just recognition. We should rather go for reasoning. This means we should check causalities instead of correlations. We should take care of spatial temporal relations of these kind of objects, going to the really next step. And for geo-related applications, then of course transferability of the models is very important. And everybody is aware that if we use a model trained in Europe, it will not ideally work for Africa, for instance. And how to tackle this issue is very important. And another point here is, for instance, automated deep topology learning, because we should not waste our time sitting in front of the PC for tuning hyperparameters. We should try to automate most of the processes. And in remote sensing, we have very limited annotated data. This means we need really smart architectures that are robust against labeling noise, less demand to the annotated data. And for Earth observation, how to quantify the uncertainty is the key, and so on. Of course, another very important aspect is benchmarking. So every day there might be 5, 6 deep learning approach published in the community or even more. And how could you to compare all these kind of methods? So I think here we're just in the opposite of the computer vision community. We need much more benchmarking in the community. Well, as I said, this was the agenda, and today I focus on 2 things. The first thing is about open data in AI for EO. Let me cite again, everybody needs good labeled data. And today, very specifically, I will announce 3 of the benchmark data sets which are recently made available from our lab. And the second part is social good application. I think it's very much in line with this conference's idea. And so let's start with the first part. Maybe I should rename it to 3 golden AI for your benchmark data sets. And the first one is about, we call it a set LCZ42. And this is a data set we generated to map the local climate zones. So this is a classification schema which is originally proposed by the urban climatologist. It describes basically how compact an area is, how high the area is, and the percentage of green and so on. Scientists use this kind of maps, for instance, to identify heat islands in urban areas and so on. And basically what you can see here is how this data, how these classes looks like in the radar and optical data. And what we did here is we selected about 42 cities across the globe covering 10 different cultural zones. And we did a very lengthy calibrated process to hand label these 42 cities to get these labels. So after the labeling, I think this is really unique. We let 10 experts to vote for these labels. This means along with the labels, you also have the quality measure of the labels. So basically here is the most expensive matrix I produced ever. This is the label confidence matrix. This means actually how sure we are for these labels we're providing. And here is some key features. In the end, it results on more than 400 pairs of Sentinel-1 radar, Sentinel-2 multispectral data with these LCZ labels and the label confidence. And different from many other benchmark data sets, this is truly hand-labeled. This means you don't have to think this might be some black box classification maps behind. And also, I'm happy to say this is for the first time that we have a data set with such a quality measure of label uncertainty. So this, of course, can be used for benchmark for image classification, data fusion, very importantly, the qualification of the uncertainty. And since it's a very large-scale data, it can, of course, also use for instance, computing in AI if you want to train large models, and also for AutoML. The second data set is SEN12MS. It's a complicated name. It's a large-scale benchmark for data fusion, where you see Sentinel-1, Sentinel-2, and land-use and cover maps. And it has selected from more than 250 locations on the Earth, and up with more than 180,000 triplets of this data, and this can be a suitable benchmark if you want to do data fusion. And this data is currently being used as the basis for this year's IEEE GISS Data Fusion Contest. The task is for global land cover mapping based on weakly annotated samples based on these data sets, and it's still running. The test phase will start from March the 1st, so if your students are interested, this is a very nice opportunity to win a nice GPU in Hawaii. And the last data set I want to share is the ERA data sets, which is area videos where we try to provide a benchmark to recognize events from such videos. So altogether it's about 3,000 videos in 25 event classes. So you can use it for, I think can be both relevant for the remote sensing and the computer vision community. Well, this is a quick share of 3 data sets. I probably only still have 10 minutes time. I will go to the second part of the story, which is the social good application global urban mapping. Obviously, it's relevant to the no poverty and the sustainable development of cities, these 2 SDGs. I think it's known to everybody we are living in an urbanized planet. And what you might not know is that since about 2014, for the IPCC report, there's a first time a chapter on urban area. This basically highlights how much we're impacting the climate change. And another thing which you might also not know is if you look at the geographic distribution of urban growth, they're mostly happening in the developing areas, which is Africa, South America, and Asia. And if urbanization is not very well controlled, this could be a big issue. Here is an example in Mumbai. Basically, in the last 10 years, there were about 50,000 fires in this city. And what is really astonishing is about 70% is simply because of the faulty wiring in such urbanized areas. And of course, if you want to improve the situation, the first thing you need to do is have geo-information. Here is a counterexample of Lagos, where we have more than 20 million population, but for such a city, we even don't have 3D maps. And if, well, golden age of maps, but not for everywhere. If you want to know what is the actual current state of the art, one example is the global urban footprint, which is produced by our colleagues in 2012. Which is a boundary map of urban and non-urban, the continuous effort in the community. Now we have the human settlement layers where you have more classes, but still it's still on 2D. There's nothing which is really available on a building level. So actually in the project, what we are doing is we are fusing about 10 petabytes of data from different sensors, also social media, and we try to derive on a building level 3D, 4D urban models, infrastructure types, and also population density. And the idea is that if we use radar, if you're familiar with it, we are able to use interferometry to get the 3D model of the buildings. And of course, if you have planet or multi-superspectral data, then you can get the roof material, building footprints. And what is more interesting is if you have social media data, you add another perspective from the ground. It tells you more information about the functions of the building. And you can also string tweets sent from different geolocations, from the time and the space where it's sent. You can also get a clue about the functions of the buildings. And of course, this is the concept. In the end, if you're dealing with global data, then it's about 10 petabytes of data. And I would like to just quickly show some of the results we have already achieved using AI and the data science. The first part is about global 3D, 4D urban mapping. And to give you a reason why we are bothering about this, we are talking about open science and open data. If you think about building information, you probably think about OpenStreetMap. To give you some numbers, on the Earth we have about more than 3 billion buildings, and only about slightly more than 300 million we have the building footprint, which is less than 12%. If you talk about building height, then only 3% of these 300 million have the height, so which is actually less than 0.4% of all the buildings. So what we do is, I showed the planet video. We have been using planet data. You know, they have a 3 meter to 4.7 meter resolution depending on which product you are using. However, if you would be able to use really sophisticated deep learning algorithms, in this case we use graph convolutional recurrent neural networks, and using OpenStreetMap as the ground truth, then finally we can train a model which can produce from such a relatively poor quality satellite image to get this kind of building footprint. And of course, if you're using kind of a multitasking network, then you will also be able to get the building instance. And currently we are processing about 28 million kilometers square of planet data, try to get it on a global scale. And, but this says nothing about the 3D. And for the 3D, we are making use of the German TerraX 10X mission. So we are in Berlin. Basically, this is how the radar image looks like in TerraX. And you know that radar is looking to the side, but each of these images are providing a distance information in the face. And if you combine actually data from different angles, you're able to get a kind of a tomographic reconstruction of the Earth's surface. This is what we call the X-ray of the Earth, because it's quite comparable to CT. And with tens of images with a lot of computing power, finally we are able to end up with this kind of reconstruction. Color stands for the height. Well, you see this is the Potsdamer Platz. We are about here, and this is Berlin Central Rail Station. And we have a point density which is about 1 million per kilometer square. And this is Siegersäule. My favorite example is always this lamppost along the roads. Well, if you have meter resolution data, a lot of them, I would say the job is quite easy. The computational power is the problem. The reality is, if you talk about global reconstruction, then we don't have TerraX in half meter resolution. Instead of that, we have 10x. We have 3 meter resolution instead of half. And we don't have tens of images. Probably we have up to 5 images for every areas. So here is basically showing how in a year the 10x mission can cover the globe. And of course, per definition, when it starts, we don't have that many images. And then we are using really a data science approach. So using X-ray of the Earth with such a less quality data, we're able to get the building height reconstruction. If you can still recall, I'm using planet data to get the building shapes. If you combine these two information, then this is basically the first impression of the global 3D urban model you can achieve. And in this case, it's Munich. We compared about 30,000 of the buildings. Basically, the accuracy is better than 2 meters. And in about 2 years, we will then produce global data sets, which is also including all cities in Africa. And this still does not say much about settlement types. And the idea is to figure out where are the residential, commercial, and etc. The truth is this is so culture dependent, it's very difficult to one step go there. That was actually the reason why we started this morphological mapping using the so-called local climate zones classification, because if you have a very high-rise compact areas, this is the case of Vancouver, then it's reflecting the city center. If you are talking about lightweight, low-rise, which is one class in the local climate zones, this reflects our understanding, for instance, of the slums. So we have been, for instance, if you talk about architectures, if you have seasonal optical data, it's very natural that you use stacked convolutional and recurrent networks for doing this. And basically, with about 4 petabyte data, you will be able to achieve this kind of global open local climate zones classification. And more interesting is, of course, the urban areas, which is just reddish here. And you can see many of these local climate zones classification. Instead of showing this, I just show you one concrete example of Munich. So you will see on top of the 3D model we reconstructed, if you see very reddish area, these are the compact area. If it's orangish areas, this is more rich areas. You have a lot of green with small houses and so on. So we are, basically this data is already globally available. And the last part, it's about how to tweet for social good. So I'm not sure how many of people here are tweeting, but I suppose not too many. And how can we actually get building functions from tweets? Let me show you one example. So this is residential, non-residential mix, 3 rows. If you just look at the time chart of the tweets, you will see people have totally different tweeting behavior at different areas. For instance, people tweet much less in the daytime in the residential areas. And for the mixed use, basically these are the shops. You can see exactly when the shops are open, when they're closed. Of course, this kind of information can be used to get the functions of the buildings. And on top of that, different topics are discussed at the different areas. So even for topics that are of joint interest, like jobs, they are usually discussed on different contextual information. If you use an LP to get the text features and combine this kind of spatial temporal feature and the text features, this helps us to get the building functions. And basically this is the preliminary results where you see residential and commercial area from OpenStreetMap, and this is what you can predict from tweets alone. So you can see actually, okay, it's possible to go back. Even though the information density is not that rich because not everybody is tweeting, but the long trivial pattern of commercial area can be very well captured. And from the study of the project, we are doing streaming. Currently, we are having about 300 million precise geolocated tweets, and we are aiming at getting this on a larger scale. And of course, I think this is trivial. If you have a great ground view of social media images, you can, of course, better decide which kind of function it has. So if you would have a library of a lot of images with the functions, you can use any kind of machine learning models to produce a very nice, let's say, building function mapping. And we are currently streaming about 45 million of social media images. This is how they are distributing, how to get in from such unstructured data to be valuable geoinformation that are useful for the society is, of course, a very big step. This is still progress. And our vision in about 3 years is that we will be able to produce a first and a unique global and a consistent spatial data about urban morphology. This means if you would go to any city like Mumbai I showed before, you will have go beyond what you have this 2D information. You can get to know where the slums are, and if you want to improve certain areas, you will also have 3D information as well as the population density accessible. And we will also make this kind of data open to the society because we really want to lead to a better understanding of the global change process of urbanization. And this kind of information, of course, is very important for stakeholders if they want to make the strategical decisions about urban development. And of course, this is also, in our humble opinion, a small hand to help the poverty problem, all in all, where the information needed is more the developing areas. And this is basically this project team. Well, this is just the beginning, so I'm just showcasing one of the examples where AI data science can contribute. But you know, with Earth observation data, we can actually contribute to other things like Earth system research, global change research, meteorology, as I was mentioning, to provide indices for SDGs and etc. Okay, so I think that's all. Thank you.
Thank you so much, Xiaoxiang Zhu.